Hello everyone, this is Wang from the Google Speech team. Today I'm going to talk about our recent work on fully supervised speaker diarization, also known as say goodbye to clustering. First, let me start with some introductions. Before you continue watching this video, I would highly recommend you to watch this video first. Just search speaker diarization with LSTM in YouTube and you will find it. This video talks about our baseline system. It also gives an entry-level introduction of speaker diarization in general, like what problem it's trying to solve, why it's important, and how it's different from other tasks like speaker recognition or speaker change detection. So please make sure you watch this video first. Okay, now I assume you have watched that video. A brief recap. What's speaker diarization? It's the process of partitioning an input audio stream into homogeneous segments according to the speaker identity. It solves the problem, who spoke when. Almost every speaker diarization system makes use of a speaker recognition system, and the modern speaker recognition systems are embedded learning systems. It encodes a fixed length segment of audio into an embedding vector, known as the D vector, using a neural network like LSTM. This is the diagram of our baseline system. First, we extract overlapping sliding windows. Then, we run LSTM on each window. We aggregate the window embeddings into segment embeddings, and we cluster those segment embeddings to produce final diarization results. Okay, now we have briefly reviewed the baseline diarization system. Let's focus on one of the most important components in the system, the clustering algorithms. Our claim here, for speaker diarization, clustering algorithms are not good enough. I will explain why next. Here is a list of clustering algorithms that have been used for speaker diarization. Gaussian mixture models, mean shift, hierarchical clustering. These are pretty old school algorithms. K-means, this is probably the most popular algorithm for speaker diarization. Although it's very simple, it actually works pretty well on many tasks. Then spectral clustering. This is the algorithm that gives the best speaker diarization performance on many of our benchmarks. It makes use of the global structure of the embedding space, which is the biggest difference to other algorithms. Here is a figure that I took from the scikit-learn official website, demonstrating the performance of several clustering algorithms on some typical cases. All these algorithms are mostly offline clustering algorithms, which means you can only perform the clustering when you have all the data ready. Some of these algorithms have their online version, but the performance is usually much worse than the offline version. Then let's look at an example here. Assume we have this data point in a 2D space, which is kind of a bow tie shape. How many clusters are there? Well, it's hard to come up with an answer that convinces everyone. You can say there are two, because this bow tie shape has a left half and a right half. You can also say there's only one, because the two halves are connected to each other. But what if I give you an example? Let's say this is an oracle, telling you in this example, we have a ground truth clustering result, which has two clusters. Then I guess everyone would agree in the original data, there should also be two clusters. But with the same original data, what if I give you a different oracle, telling you in this example, there is only one cluster? Then for the original data, we came to a completely different conclusion, that there should also be a single cluster. Now we see that for the same data, we can end up with different clustering results, depending on what we store in a training dataset. Okay, let me show you something even more interesting. Even without training examples, what if we know the order of the points in the original data? In the first case on the left, the points appear in the left half first. then appear in the right half. In a conversation, this is like one person talks first, then another person starts talking. In the second case on the right, there's no clear pattern on the appearing order. Looks like the entire set is an entity. So, given this knowledge, we are leaning to believe the first case has two clusters, according to the appearance order, while the second case has one single cluster. Now we've seen what standard clustering algorithms cannot do. First, they cannot learn from examples. They are usually based on heuristics and rules, not based on data. Second, they cannot incorporate temporal information. Most of these algorithms are order agnostic. Speaker diarization is a speech problem. Let's see what inspirations we can draw from other speech problems. In speech recognition, people are using frameworks like CTC, listen, attend, spell, and sequence-to-sequence learning. In speech synthesis, or TTS, the most successful work, Tackletron, is also sequence-to-sequence learning. In machine translation, the most successful work, Google Neural Machine Translation System, is also based on sequence-to-sequence learning. What they have in common is that, first, all these techniques are supervised. Second, they all use recurrent neural network. And finally, they are all trying to design a loss function that describe the end-to-end performance of the system. So how do we make the speaker diarization task also a supervised problem? We first need to understand what are the supervised information that we can use. In a speaker diarization training set, apart from the speech signals, we usually have time annotations of many segments. Each segment has a start time, an end time, and a speaker label telling us who spoke this segment. Our mission is making full use of these speaker labels, together with the timestamps in the training data. If we only use the speaker label, we are doing supervised speaker recognition, not diarization. We can only claim we are doing supervised diarization if we are using the timestamps as well. Also, it's important to know that, although in general, such timestamped labels are expensive to acquire, but in some specific domains, it's relatively easy, such as phone calls, where different speakers are recorded in different channels. When we submit our paper to ICASSP, one of the reviewers says, there are many scenarios when your assumptions are wrong and supervised diarization is not going to work. Well, we have to clarify that supervised diarization is not a hammer for all nails. If you want to train a supervised diarization model in one domain and expect it to work on every diarization dataset, you can basically stop watching this video now. It's not going to work. This is not a problem for speaker diarization. It's basically for all supervised learning problems. For ASR, you cannot expect that you train an ASR model on telephone speech data only and expect it to work well on YouTube data, right? Okay, so much for clustering. Let's get into the hardcore of the paper, UIS-RNN. First, let's start with the notations. We use X to represent the sequence of observations. Each sequence has all the embeddings for one utterance. We use Y to represent the sequence of labels for this utterance. Each lowercase y is an integer, as the speaker ID. We use Z to represent the binary delta between neighboring labels. If the labels are different, then Z is 1. If they are the same, then Z is 0. Let's see an example. If an utterance has 6 embeddings, then it also has 6 labels, which is our Y here. Given Y, we can infer Z. The first element in Z is 0 because the first 2 elements in Y are the same. The next Z is 1 because the next Y changed. Z can be uniquely determined from Y, but Y cannot be uniquely determined from Z. Our target of UIS-RNN is to model the joint probability of X and Y. We also include Z in the joint probability, such that we can decompose each term into three components: sequence generation, speaker assignment, and speaker change. Now, let's look at these components one by one. First, speaker change. Speaker change is a distribution to model how likely the current speaker is going to change to a different speaker. In the generic form, we assume at time t, the binary change indicator zt is the distribution conditioned on previous changes, and the distribution is parameterized by lambda. This distribution can be anything. For example, it can be a recurrent neural network. To start with, we use a very simple form. We assume each z follows an independent and identical distribution, which is a coin flipping process. In this case, there is a single parameter p0 for the head of the coin. Okay. Next, speaker assignment. If the speaker has changed, we still don't know which speaker it is. It can be a new speaker that we've never seen before, or it can be one of the speakers that we've seen previously. To model this distribution, we use the Chinese restaurant process. Here is a brief demonstration of the Chinese restaurant process. You come to a restaurant, and there are three tables that have been occupied. Which table are you going to join? If none of the three tables are your friends, you will sit at a new table, waiting for your friends, because you are the first to the party. If one of the three tables are your friends, then you will join them. As an observer, I guess you will most likely join table 1, since they have the most people and their party has started for a while, waiting for the next person. Let's use a mathematical language to describe our intuitions. If speaker has changed, we assign it to a new speaker with a probability proportional to a constant alpha. We assign it to a previous speaker with a probability proportional to how many times that speaker has spoken before. Each time a speaker speaks, he makes a block, which is a continuous subsequence of the same speaker label. So why are we using the block concept here? What's the heuristics behind this distribution? We can understand it this way. If a person is leading the majority of the conversation, we believe he is very likely to speak again. If a person often interrupts others, we also believe he is very likely to jump in again. And we also believe a new speaker would appear with a stable probability given a domain. For example, during a phone call, it's very unlikely a third person will jump in. For a meeting, well, it's mildly likely. But for a movie or a TV show, it's very common that a new character will join the scene and start speaking. Okay, we talked about speaker change and speaker assignment. Finally, let's look at sequence generation. Basically, we want to model X given previous X and Y. We have three assumptions. First, we assume each speaker's embeddings are generated by an RNN instance. Second, we assume for different speakers, their RNN have the same topology and parameters. However, we assume each speaker's RNN has its own states. Assume this network has some GRU layers and an output layer. The set of parameters of all these layers is theta. The GRU input depends on the last time we see this speaker before, and we assume the observation follows a Gaussian. Now, let's put all components together and give a summarization. At any time t, assume we have seen k speakers already. There are k plus 1 possible paths in total. It can be a new speaker. Then we are going to create a new RNN instance and initialize it. It can also be a previous speaker, including the last one we've seen. If it's a previous speaker, we continue updating that speaker's RNN instance. Now I think you should understand why we call it UIS-RNN. The full name is Unbounded Interleaved State RNN. Unbounded means that with Chinese restaurant process, we can produce unbounded number of speakers. We don't need a separate model for a number of speakers. Interleaved state means that we have many RNN instances, and their state will interleave in the time domain. Okay, the next important question is, given the training data of n utterances, how do we train a UIS-RNN model? The short answer is we maximize the knock joint likelihood. This is known as the MLE estimation. We can break it down into different steps. For the speaker change, P0 can be estimated independently and deterministically using just the speaker labels. The other parameters, like the alpha for Chinese restaurant process and the GRU parameters, they can be learned by a gradient ascent. You may ask why it's a gradient ascent, not a gradient descent. Well, it's because we are maximizing probabilities, not minimizing a loss function. Once we have trained the model, we can use it to decode new utterances. Given a test utterance, we want to find the neighbor sequence Y, which maximizes the knock joint probability. If we search the entire solution space, the complexity is t factorial, which is impractical. So in practice, we use an online greedy decoding algorithm whose complexity is big O of t squared, or big O of t if we add an upper bound to the number of speakers. For better performance, we also use beam search and look ahead during the decoding. Okay, that's all for UIS-RNN. Let's look at our experimental results. First, we made several improvements over the previous D-vector models. We are now using more training data, such as non-US English data, far-field microphones, and public datasets. We also used an important trick called variable length window training. Our new D-vector model V3 is now much better than the baseline V1. The evaluation protocols for diarization. These are some of the standard practices. We are using the pi-alloc matrix library. We exclude overlapped speech since we are focusing on diarization, not source separation. We tolerate errors smaller than 250 milliseconds. We report confusion errors, which is referred to as diarization error rate in other papers. Datasets. We are using 3 datasets. The list SRE 2000 has 8 disks. Disk 8 is called Core Home. This is the evaluation dataset used by almost everyone. Disk 6 is called Switchboard. There's also this ICSI meeting corpus. Remember that we are doing supervised diarization, which is different than any existing work on speaker diarization. So our evaluations are also kind of more complicated. That's why we have 3 different setups. The first setup is in-domain evaluation. We only use disk 8, but do a 5-fold evaluation. We divide it into 5 subsets. Each time, we train on 4 and evaluate on the last one. Then we repeat this process 5 times. The second setup is off-domain evaluation. We train on disk 6 and ICSI. Then we evaluate on disk 8. The last one is in-domain plus off-domain. Evaluation is still 5-fold on disk 8, but training will also include disk 6 and ICSI. Here are the results. So what can we learn here? First, UIS-RNN is apparently the winner, much better than k-means or spectral clustering, even if UIS-RNN is online, while the others are offline. Also, by adding off-domain data, UIS-RNN can improve. This is because UIS-RNN is supervised, so it can benefit by learning from more examples. Besides, we see that off-domain training also has good results. Also, The differences between different D-vector models are big, especially the variable length window training, which is D-vector v3. Finally, UIS-RNN has the state-of-the-art performance compared to previous work. Okay, now let's spend some time to look at the Python library. We have open sourced this UIS-RNN library on GitHub. It's based on Python 3 and PyTorch. We designed a similar API to the standard scikit-learn library. We have a test coverage of more than 90% of the code and enabled continuous integration. We have provided detailed documentation and made the library available as a PyPy package. Here are the most important APIs you will be using. First, for your main Python program, you will need to parse the command line arguments. We have this parse arguments function for you. You will get the arguments for model, training, and inference separately. Next, you construct your model by initializing a UIS-RNN object. Once you have the model, you call the fit function to train it on your training data. After training, you use the predict function to run inference on your tested data. Besides, there is a save and load function for you to store a trained model on your disk. To use the fit function correctly, you need to prepare your training data carefully. The train sequences here should be a list of sequences. Each sequence is a 2D NumPy array. Each row of the array is an embedding, like a D-vector. The train cluster IDs here is also a list that has the same length as train sequences. Each label sequence is the list of strings, where the string is the unique ID for the speaker. The program supports many command line arguments. Here I want to explain two of the most confusing ones. First, the enforce cluster ID uniqueness argument, which is the training argument. Since the train sequences is a list of sequences, each sequence has a corresponding label sequence. If we see the label, for example, letter A in two different sequences, do they refer to the same speaker? If the answer is yes, then they already guarantee global uniqueness, so we can set this to false. But if the answer is no, they are different speakers, but with the same name across utterances, then we set this to true to make them globally unique. Another argument is called test iteration. This is the number of passes for decoding. For example, if it's 2, then we concatenate the test sequence 2 times and decode. Then take the decoding result of the last one after concatenation. So the decoding is only online if this value is 1. Okay, since lots of people ask us questions by sending us emails or filing issues on GitHub, here I want to answer some of them in this video. First, some people ask, can I directly feed in audio waveforms into the UIS-RNN library? The answer is no. The inputs to both training and inference must be speaker discriminative embeddings, such as D-vector. Second question, how do I compute the embeddings? There are lots of third-party implementations. If you don't know any of them, I made a curated list of resources called Awesome Diarization. Please check it out. Another one, which dataset should I use for training? Basically, any dataset with both speech and time-stamped speaker labels will do. Also, each utterance must have more than one speakers for sure. I also listed many public datasets on the Awesome Diarization website. Which one you should use? It really depends on the domain that you want to deploy this system. Some more questions. Some people read the paper and ask us, UIS-RNN is complicated, but the improvements seem to be very small compared with spectral clustering. Is it really worth it? Well, you clearly missed the one thing, that UIS-RNN decoding is online, while spectral clustering is offline. We have implemented several other online clustering algorithms. They are much worse than spectral clustering or k-means. UIS-RNN is an online algorithm, and it's even better than the best offline algorithm, so that's amazing, right? And it still has the potential to improve by adding more training data. Next one, many people ask us to share our data, code, and model for the speaker recognition system. It's not that we don't want to share it, we really can't do it. Our data are mostly sensitive and proprietary data that are not supposed to be shared. Also, our speaker recognition system heavily depends on Google's internal infrastructure, which makes it impossible to open source. Even for the UIS-RNN library, we've worked really hard to make it open source, to make sure everyone can use the newest technique we developed at Google. I hope you can understand that. Next question. Some researchers read our paper and told us that it's a bit confusing who generated the D vectors, since there is the speaker recognition network and there is also this UIS-RNN sequence generation. Yes, this is indeed very confusing. The D vectors are always computed by the speaker recognition network, but once they are computed, we treat them as observations, and we use UIS-RNN to model them as the generation process. Let me use a metaphor here. The D vectors are like the pixels in image segmentation. The pixels are actually generated by an imaging device, but later we model the generation of those pixels using a hidden Markov random field. So it's basically the same idea. Okay, finally, conclusions and future work. Let's summarize the contributions of this work. First, we proposed UIS-RNN, which is a general machine learning model that can be trained to segment and cluster temporal data by learning from examples. By making use of UIS-RNN, we described a framework for doing fully supervised speaker diarization. Our system has the new state-of-the-art performance on the Quan benchmark, and at the same time, is an online algorithm with offline quality. Several directions for future work. First, our current speaker change model is super simple. It's just a coin flipping process. We may want to replace it with an RNN to see how much we can improve. For speaker assignment, the value alpha in Chinese restaurant process is a constant. We may want to make it also a distribution to add some complexity. During the training, we currently only make use of annotated data. What if we have a mixed source of annotated and unannotated data? Can we make use of that? This needs some research. Finally, can we further improve the performance by using a more complicated offline decoding algorithm? This is also very interesting and promising. That's all for this lecture. Let me know if you have more questions.